So the advantage of this is that it treats the dynamics as a black box. And it's very useful when you don't have access to the equations of the system. An example of this is when you use a simulator. So an example is we wrote down x1 dot equals x2, x2 dot equals u. So I explicitly coded that. But if you were supposed to do that in MuJoCo or any other simulator, then what you will do is you'll model the system with a sliding joint, right? Sliding joint will give you motion in the x direction, and then you will basically get access to the data or the position velocity at each instant of time. But you can supply it with whatever torques you want or whatever forces in this case, but you will not have access to the equations. Now that's very trivial for a simple pin joint, but if the system is more complicated, then the equations are not that simple. So when this is not available, what is available to you is this black box, which holds the simulator, which has x double dot equals u. So this, by the way, is also x double dot equals u. I just split it into two equations. What you can do in the simulator is you can provide it with inputs. You can provide it with the control, and out will come right? At every instant of time, you have full control over what you can send. However, you do not have control over x1 t and x2 t directly. It's basically what the simulator is going to predict based on your integration and so on. Okay, so in this case, we can actually, the way we'll deal with this is that we'll assume that a simulator we can pass in x1 0, x2 0, and then we can provide time histories. And then out will come x1 at t, x2 t. So if you use, so it's called a simulator. So if you use the simulator in the fashion described the first case, this is what is known as the multiple shooting, and this is single shooting. The difference being that in multiple shooting, what you'll do is you'll take the state at each time and then output the increment or new x, and then you'll use that in some way for the constraints. But in this case, you just apply all the u's and the x's at time, x is at time 0, and then all u's at all time intervals, and then out will come the state after time t. So I will show you how to do this, but you will see that extension to multiple shooting is kind of straightforward. So we'll be doing something like this, where we'll treat that box. You can submit all the u's, and out will come the state 10. So here is how you formulate it, and then of course I'll show you code which does the same thing numerically. Okay, so first thing is let's choose n grid points. Okay, which is very similar to collocation. There's no difference here. So assume that this is your time axis. Then you'll choose t t plus delta t, so on till, so let's just make it 0. It just makes it easy to write. So t equals 0, dt, 2 dt, 3 dt, so on till n minus 1 dt, which is also the final time. And then what we'll do here is we'll choose controls, which are first start off with some random guesses, and then the optimization will actually choose the right values for these controls. u0, u1, u2 till un minus 1. Okay, so these are unknowns. Okay, so the optimization variables are as follows. We have u. First, we'll have time, that's unknown, u0, u1, so on till un minus 1. Okay, so this is going to be slightly different from collocation, where we not only had t and u, but we also had the state. Next is to define a cost. Okay, here we're minimizing minimize t, so the time. Okay, then we have constraints. Okay, so I wrote down them earlier, but they are x of x1 0 is 0, x1 at time, let's just put x2 at time 0 is 0, so it's position velocity. Then we have x1, which is the position at time capital T, which is the end, is the distance you're traveling, which is 5. So I should just put it, oh yeah, that's fine. Capital T is 5, and x1 dot, or x2 at capital T is 0. So the velocity is 0. Now, we do not really need to specify this because this is ensured in our simulator. What I mean by that is we have the choice to start the simulator in any state we want. So we've just started with 0 speed and 0 position. So we can just eliminate those. This, however, will come from the simulator as an output. So when we send it the initial state, the controls, and the time, by integrating it over several time spans, it will give us what the state is of time capital T. Okay, so now before I show you the code, here's the interesting thing, which is, I think you want to appreciate this, that I should write this down. So we have one optimization variable and n for the controls. So the total number of optimization variables are n plus 1. And then for here, we only have 2 constraints. So we have n plus 1 optimization variables and 2 constraints. Now let's compare that with collocation. So in collocation, we had time, the controls, which are n, states, so we have 3n plus 1 variables. So a lot more variables in collocation. The objective was the same. The constraints, if you look at the constraints, we had 3n plus 4 constraints. They're the equations which we'll have to satisfy. So you do a whole lot of calculations in terms of constraints and optimization variables in case of collocation. While for shooting, we only have n plus 1 variables, sorry, n plus 1 variables and just 2 constraints. So let's see how this thing is programmed. We are going to use Python, and I'm going to show you using one of the integrators. I think it's from MuJoCo 4.5. Okay, so x dot and u. So u is more interesting. You saw that was +5 maximum acceleration, and then 0, and then it all is decelerating. Can just change this to pause for a bit longer. Okay, so bottom one, as I said, is maximum acceleration +5, and then go -5. And then this is because of discretization. That is, if you, because I have 5 there, because I have the grid size of, I think, 5, you get that issue now. What goes into the code? Well, as I said, I have, in this case, I have the cost, which is right here. There is the nonlinear functions, which make up for the simulator, the integration. So I need to invoke a simulator, and the simulator is nothing but just takes these equations. It's a simulator. Basically integrates the equation using ODE. So I give it a start point, which is 0, and then I integrate for all over the time, capital T, which is also unknown. And then I take the state at the end, and then I return the state. That state will be a part of so xn, which is the final position. Sorry, zzn comma 0 is the final position. Zzn comma 1 is the final velocity. This minus d, which is, remember, it needs to travel a distance of d, should be equal to 0. So I'm sending something which will be equal to 0, and vn should be 0. And all this goes inside op.minimize. This is the minimizer in Skippy. I'm using a method called SQP, which is basically sequential quadratic programs I talked about last time. I need to give it a set of constraints. I need to give the bounds. The bounds are specified as limits. So I said the bounds would be so it's min is -5, max is 5. I also need to give bounds for the time. And here I'm guessing that I need to be between 1 and 5. Now, if you see that 1 and so if you give bounds which are, let's say, 6 and 10, right? Then it actually gives you a solution. But sometimes you will see that your bounds guess is wrong, in which case your optimization will say it will not terminate successfully, which means you need to go back and evaluate your bounds and give bit better bounds. If you give too bigger bounds, then you'll see that the optimization will just be doing these computations and eventually will give you an incorrect solution. So it sort of needs to be, your initial guess has to be good. You also need to give reasonable bounds. So this particular method requires you to give the constraints as a dictionary. There was another one which I talked about in the last class, which is using constraint optimization using another method called trust constraint, which is this one. Okay. So that one uses a different method, trust constraint, and then we can try what it gives. It's basically the same code. The only difference being that I call this method, obviously. I need to give the constraints slightly differently. It doesn't accept dictionary. It accepts constraints as objects. There it is, op.nonlinear constraint versus a dictionary. And I just run this like usual, and let's see what it gives. I think this one takes a little bit more time than the first one. So we'll have to wait for a bit, but it will probably give me the same solution. Another thing which is sort of a variable you need to decide beforehand is the number of grid points. And the finer your grid is, the more accurate is the solution. But the problem with increasing the grid size, here I chose 5, if you chose a grid size which was way big, let's say 100, your solution is going to be very accurate, but it may take a long time. And sometimes it will not even give you a solution because it's just found there were too many variables to optimize over. Pretty sure this works. It will give us a solution. Just takes time. Okay, there it is. So a similar one. You see that profile U as a function. Okay, so I'll provide all this, and then you can modify this code. And there are two methods. Now I talked about multiple shooting. All you do in multiple shooting is you just put it down there. So sometimes multiple shooting is better. So I'm not going to try code for this because here single shooting works, but sometimes single shooting does not work, in which case you do multiple shooting. What you do here is the following. Okay, so this is, let's say X, this is time. X at some dt, 2dt, 3dt, so on till n dt. So x0, x1, x2, xn minus 1. And this is multiple shooting. Okay, so first of all, your inputs or the optimization variables are going to be x0. By x0, I mean it's going to be x1, 0, x2, 0, x1, x2, where x1, x2, you can see that they are the starting points at time t, dt, and so on. And then when you have, so this is the optimization variables. When you want to enforce constraints, what you do is you ensure that x end of 0, what I mean by that is after you integrate the equations for 1 times spin for, so you just put it as x0, it's the best way to do this, x, let's use a different notation here. So let's say that when you integrate this equation, you get x bar of 0, is x1. When you integrate this, you get x bar 1, x bar 2, and so on. So x bar n is obtained, or x bar I is obtained by integrating equations from starting from xi. So you have xi, you know the state at xi because that's something which you start off with. You know what the control is because that's also an optimization variable. You integrate this for a simulator, it will be just inputting those and stimulating over one single time step corresponding to dt. And once you do that, in your constraint, you will say x, if you see here, for this multiple shooting to work, the end of x bar 0 should be equal to x1, and x1 bar 1 should be x2, and so on. So you'll add these constraints. X x bar of 0, that is the end of integration of the first time step, should be equal to x1, x bar of 1, end of integration of 1 should be equal to x2, and so on. So what happens is, by doing multiple shooting, you basically added a whole lot of new variables, which will mean that it becomes sort of like collocation, but the advantage of multiple shooting over collocation is that you ensure that your equations are satisfied to integration tolerance over this whole time span. So it's more accurate than it is with without using collocation, which just satisfies it to order 1, because Euler's method is only accurate to order 1. Okay, so we will not really do this, but if you're trying to do a more complicated problem, you care about accuracy, you want to do multiple shooting.